It's a pleasure to have him here among us to give the online seminar. I hope we will see him in Bombay one of these days in real person. Jack works in many interesting themes in commutative algebra. Of course, characteristic P techniques, symbolic powers, and singularities, and differential operators, and many other things. It's very interesting to read his work. So I now invite Jack to deliver his seminar. It's a 1-hour seminar. We will have questions and answers at the end of the seminar. But during the seminar, you can write your question in chat box and I will transmit them to Jack. So I request everyone to keep the video and audio off during the lecture, and we can still interact through the chat box. So Jack, you may please start the seminar.
Great. Well, first, let me thank the organizers for having me speak in this seminar. It's very nice to have this opportunity, and thank you especially for the very kind introduction. So today, I'm happy to be talking about some joint work with Val Hoxer, but I'll also try and give some background and some other results related to this general question on when top local cohomology modules are faithful. And well, before we do that, I'll give at least a bit of a refresher on local cohomology. Quick, something that you think about often, or if it's something that it's new to you. Yeah. All can get, unless I say otherwise, and I might at some point. Okay. Oops. So let me just say a bit about local cohomology, some basics to start off with. So given an ideal and a generating set in some ring, and an R module. The local cohomology modules of M with support in I are defined as the cohomology modules of a certain complex. Each term is a direct sum of localizations at one element. Those elements will be products of our generators. And just to make sure we match the, oh, that's a T. That's a T. Okay, just to name the cohomological indices so that there's no confusion. There they are. Okay, so this, a few basic facts about local cohomology. The way I wrote it, I chose a generating set, but this depends only on I, the ideal. Well, and M, but I'm not going to write that. And moreover, if I chose another ideal that had the same radical, I would get the same thing. If I fix an I, then this is functorial in M, maps of modules induce maps of local cohomology modules. And it's cohomology theory. It's short exact sequences induce long exact sequences. And one property that's obvious from this first fact and the definition is that I can use these to give a bound on the least number of elements that generate an ideal that has the same radical as I. Well, that has to be greater than or equal to the largest I for which I get a non-vanishing local cohomology module. Otherwise, if I had some F's that made this false, then this sequence would be too short. The sequence would end before there was some place I was supposed to have cohomology. Let me take this opportunity to name this maximum. We'll call this the cohomological dimension of I. So already, just from these basic observations, we can vanishing and non-vanishing relates to interesting properties of the ring or the ideal. And now let me name some other interesting properties that this is related to. The first non-vanishing is also interesting. It's the maximal length of a regular sequence contained in I. If I have a maximal ideal, or let me just say the maximal ideal in a local ring, then I can name this top non-vanishing, and it's the dimension of that local ring. Okay, though for non-maximal ideals, this cohomological dimension is sometimes harder to understand. And another one that I like, vanishing of local cohomology, at least in this analytic situation, is closely related to vanishing and non-vanishing of actual cohomology, or the topologist cohomology, let's say. So if I vanish for I at least t, then the topologist cohomology, singular cohomology, let's say, of complex D space, take away the variety of I, and take the analytic topology. Then that will vanish for, well, I at least t, or D plus I at least. Yeah, okay. Great. So the vanishing and non-vanishing relates to things of interest. Also, there are useful invariance properties that make this somewhat easier, or that are advantageous in computing. Let me just single out the change of ring property, as it's sometimes called. If I have a ring homomorphism, an ideal of R, then, well, there's two local cohomology modules that kind of, or two ways of computing local cohomology that kind of jump out. One is by considering S as an R module. And the other is by considering I as an ideal of S by extension. And these two things are canonically isomorphic. And so if we have a ring map, we can freely expand. Okay, but for all of these great vanishing things and great invariance things to be true, the cost is that the objects are big and harder to understand. Oops. So in particular, they generally fail to be finitely generated modules, even if you plug in a finitely generated module for M. And yeah, if there's one local cohomology module that everyone should see if they haven't seen one, in my opinion, it's the local cohomology of a maximal ideal in a polynomial ring. Let me write it in terms of a K vector space basis. So I want to think of it in terms of vector space basis of monomials, but where every exponent is strictly negative. So when we see this, then there's a natural and obvious way that the polynomial ring should act on this. Right? We just we break our polynomial into monomials. We multiply monomials by monomials. And of course, the catch is then that if I get a new monomial where now one of my exponents is non-negative, then it's 0. Okay, that's the action here. Okay, this in particular is not finitely generated. I'm going to need more and more negative alphas. I need my alphas to be larger and larger as negative numbers to generate the whole module. Okay. Okay, so that's the basic things I want to recall about local cohomology. Let me say a bit about the general question that motivates us. So, well, there's much interest by many people in when local cohomology modules vanish or fail to vanish. Hopefully I've said enough to motivate that a little bit based on the properties that we otherwise like that are related to this. And there's also a lot of interest in the support of local cohomology modules. And so, of course, this is a question that's closely related to vanishing. Where on the spectrum do our local cohomology modules vanish? Let me also single out a very interesting question on whether local cohomology modules always have closed support. Since they're not finitely generated modules, they're not a priori entitled to closed support. But somehow it seems in all of the examples that we know that this is true. Great. So closely related to both of these is the question of what can we say about the annihilators of local cohomology modules. And of course, vanishing and support are closely related to annihilators. Let me take that as a quick and loose motivation for this question. Perhaps at the end I can give a more precise statement about how understanding annihilators of local cohomology modules can give concrete understanding about vanishing of local cohomology modules. Before that, let's just start with an example, with the example that we have. And so let me, oh, there's not quite enough room. Well, let me just circle this so we can keep it in our minds and remember it. Okay, so this was example 1. Okay, so here, any element here is killed by a large power of the maximal ideal. So this is just supported on this maximal ideal. So but this module is faithful. So this would not line up if we were dealing with a finitely generated module. The support would be the variety of the annihilator. But here with a module that's not finitely generated, we can have this seeming difference. From the point of view of support, this module is very small, but from the point of view of annihilators, this is large, okay, because the annihilator is small. Good. Let's see a couple more examples. What do I do first? All right, let's do this one first. Let's consider this subring of a polynomial ring in 2 variables over a field. The normalization is the polynomial ring. The ideal I want to consider is this maximal ideal. And when I expand this, then X and of course Y are both contained in the radical. From this, well, the quotient of this ring by this subring is a 1-dimensional vector space generated by the class of X. So there's a short exact sequence that induces a long exact sequence. Of local cohomology with support in M. Okay, so here we're considering local cohomology with in a polynomial ring with support in a maximal ideal. I guess I didn't mention here, but for everything less than D, these vanish. So these will be zeros. So here we're taking 0th local cohomology of this field K. This will be a copy of K. And so this will be isomorphic to K. This is not a faithful R module. It's annihilated by M. So H1 M R is not faithful. Okay. So we've seen an example of a local cohomology that was faithful, one that wasn't. Well, let's see at least one more that is not faithful. Take this quotient of a polynomial ring. Then we take the local cohomology of R with support in X from the check complex. We see this description, but Y kills this, and it's easy to see that this quotient is non-zero. So here's a non-zero local cohomology module that is again not faithful. So However, there are some things that are true about this example that are not in the other two. So, well, let's state a question. So to avoid example 3, I want a domain. For reasons that I'll only get to later, perhaps. I'll assume that R contains a field. And now I'm going to single out the top non-vanishing local cohomology module. And so let me, so if this notation was new to us, let me clarify what I mean. Larger ones vanish, but this one does not vanish. So this is the top non-vanishing local cohomology module. Is this a faithful R module in the sense of having annihilator 0? And here, whoops, well, we know that there's another one of these that's not 0, right? The dimension of this ring when we localize it, this maximal ideal is 2. So, so this was not a counterexample to this question either. So this is what we might hope for. Or here's an example of something that we might hope for in terms of faithfulness of local cohomology modules. Okay, so let me say that this is somewhat of a historical note. This was inspired by a question of Lynch. Laura Lynch, who was a grad student at UNL. So just to state the history and tie in with some things you'll see in the literature, let me make the state your question. So if we take the top non-vanishing local cohomology, is its annihilator small in the sense that R mod, the annihilator, has the same dimension as R mod, the I torsion part of R. Okay, but this is false. Or the answer to this question is no. Okay, so there are examples due to Bauman and Poor. And Singh and Moulter. These examples are non-equidimensional. But this question just specializes to question 1 if you take domains. Okay, because there's nothing here, and if the dimension is going to be the same, this better be 0. Great. Question 1 also has a non-domain equivalent. If you don't assume domain, then this is just insisting that the height of the annihilator is 0. That the annihilator of any top local cohomology modules contained in any minimal prime. But the heart of this question is in the domain case, so I'm going to be sticking to the domain case. So let me. So as a warm-up case, and also an excuse to introduce or remember some important facts, let me talk about the case of, well, I'm going to lump 2 cases together that are closely related. The case of a maximal ideal OR, and the case of where there's only one non-vanishing local cohomology module. Okay. So So this will be an excuse for me to recall a statement of local duality. And it'll be a statement for the complete Gorenstein case. So I'll just say local duality, though, of course, there are plenty of other, this is not a comprehensive statement of local duality. So if I have a complete local Gorenstein ring, I will name the dimension D. And I want to emphasize a certain lack of a hypothesis. So in this setting, I do not need to assume that I have a finitely generated module. Then we have the version of local duality where the matless dual is on the local cohomology side. One often finds this in the literature with the assumption that M is finitely generated, but it's just not necessary here. Okay, so one other recollection or exercise that's not familiar. If all of my local cohomology modules with evaluated at R past some index I vanish, then that local cohomology functor HI I can evaluate it at R in base change. And this is this more or less follows from the long exact sequence. So a good exercise if this is not familiar to you. Great. So with those two ingredients, we can take care of this faithfulness question in the case of a maximal ideal. Let me attribute this to Lynch because it does appear in her thesis. I don't know if in this generality if it had possibly appeared elsewhere, but at least one can find this here if you want to read about this. And also she has a more general statement than this, but so be it. Okay. So if I have a domain and I name the dimension, then this top local cohomology, local domain, the top local cohomology with supporting the maximal ideal is a faithful R module. And I want to quickly go through the proof here because, well, it's kind of fun, and also because we'll try and use some similar ideas later. So suppose I had something that annihilated the top local cohomology module of R. Well, according to this remark, then if I complete R and mod out by a minimal prime, then that local cohomology is attained from this one by base change. So this will annihilate this too. Okay, so R is a domain, R hat may fail to be, but certainly this quotient is. Now, since since going down holds here, P intersect R is 0. Okay, so if the complete case holds, R is 0 here, but then R was 0 here. And so the complete case implies the general case. So let's assume that R is complete. So in particular, I'm a quotient of a regular local ring by some prime Q. And let me take a maximal regular sequence inside of Q. Since T is regular, the particular cohomology, this maximal regular sequence has as many elements as the height of Q. Okay, so I've got a factorization like so. And now I want to take local duality over S. These have the same dimension, so D minus D. This is the 0th X we're looking at here. Great. So by construction, Q is a minimal prime of S. So R embeds into S. And that means that HOM S R into S is a faithful R module. Right? There's a copy of R. And well, matless duality preserves annihilators. I'm not going to prove that. We'll just remember that as a property of matless duality. Okay, and that's all. Okay, so that's an application of local duality that I personally enjoy. Let's extract a corollary. If I had a local cohomology module that for which there was only one non-vanishing, then this module is faithful. And let's just deduce it from the previous proposition by considering a minimal prime of I and localizing. So perhaps you'll forgive me for using an invariance property that I didn't state. Okay, but well, now the radical of IP is P. Again, this localization. Okay, so now we have now we're looking at local cohomology with support of a maximal ideal in a local domain. When I is the dimension of this local domain, then this localized local cohomology module is non-zero and faithful as an RP module. Okay. So, well, that means that this I was equal to the height of P, right? The non-vanishing one had to be the height of P for it, the height of any minimal prime of I. And if nothing in the localization kills it, then nothing in R kills it. Okay, so perhaps I'll quickly note that Lynch proved this latter corollary without without the domain hypothesis, by a pretty different argument showing that the product of all the annihilators is equal to 0, and that follows from a certain spectral sequence argument, which is also interesting, but not something that I'll say more about for now. Okay, so let me now say a little bit about some cases where, well, let me address a stronger question. When are all non-zero local cohomology modules faithful? And this is certainly a stronger question, even based on the examples that we've seen. We collected a few examples of non-faithful local cohomology modules. So we should have to assume something about our ring. Let me briefly tell us about this for strong life regular rings. So now R is a ring of characteristic P. This is strong life regular if for any C that's not in a minimal prime. I'm going to state this in a slightly different way than one usually does, but directed towards the purpose. The map C times E for iterative Frobenius. This splits as a module over the source. So this might look a little bit confusing. Let me say a little bit more what I mean. Okay, so first, ETH iterate here. This F to the E is the ETH iterative Frobenius. C is multiplication by C. And what I mean here, there's this Frobenius map from R to R. So now I want to view everything as a module over the source. Right? This R has a non-standard R module structure by restriction of scalars. Some people might be inclined to put an E here or an FE lower star. I'm just going to lean on the words as a module over the source. Okay, multiply by C. And, well, whoops. Then there's some sort of splitting from R with this restriction of scalar structure back to R. So that this diagram commutes, we get back to the identity map. Okay, so this is certainly not true for every ring of positive characteristic. But many interesting rings satisfy this. Let me just say polynomial rings over perfect fields. Toric rings. And let me just stick with perfect fields throughout. Toric rings, determinantal, and others. Right. And these satisfy the title of this section. All local cohomology modules are faithful over such a ring. Let me stick to the local case. And this argument is, I think this is essentially due to Mel. One finds it attributed to him in the regular case in a paper of Hunicke and Co., but I think it's most fair to say that this is an argument from Mel. So if we have a strongly F regular local ring, then any non-zero local cohomology module is faithful. Okay. And well, the reason I stated this in such a weird way is to make the proof really easy. Once we interpret strong F regularity in this way, we just apply a local cohomology functor. Okay. And if this were the zero map, that would contradict that the identity factored through it. Okay. So I won't even write anything, I'll just put a box. Great, so there's an excellent collection, not excellent in the technical sense. There's a nice collection of rings for which every local cohomology module is faithful. And also in characteristic 0, and this setting will also include some characteristic P rings, but let me also, well, anyways. Another class of rings where all local cohomology modules are faithful are the following. First, a little bit of setup. If we've got a field and an algebra over a field. Okay, so here I'm explicitly saying otherwise. There's a non-commutative ring of differential operators associated to this pair. So this is some sort of ring that contains, non-commutative ring that contains R and the derivations on R and perhaps many more things beyond that. What I want to say about it is that every local cohomology module is a left module over this ring. And let me recall a fact from non-commutative algebra that the annihilator of a one-sided, of just a left module, is actually a two-sided ideal. So from this, it follows that if this is a simple ring, meaning there's no non-trivial proper two-sided ideals, then the annihilator as a module over this ring of differential operators is 0. The only possibility. It can't be the whole ring if this is non-zero. Let me assume that I have a non-zero local cohomology module. Okay. And since this contains R, then it must be faithful over R. Okay. So all I want to say now about this is that this happens. This is also a very stringent condition on a ring and kind of mysterious. This happens for polynomial rings and many classical invariants. But it's still not known to hold for all invariant rings of linearly reductive groups in characteristic 0. This is a conjecture / question conjecture of Schwartz / question of Levasseur and Stafford that's remained open for some time. I think it's an interesting question, and here's some motivation for it that I like. Okay, great. Then now let me go back to the main question and get to what's new. So here's the main new result that I wanted to talk about today. So let's take a domain. Here, I'm going to bother to name the residue field of positive characteristic. And ideal generated by some stuff. And if this T local cohomology module with support in I is non-zero, and let me elucidate, there's a hypothesis here. This is saying that the cohomological dimension is equal. It certainly can't be bigger, but we can achieve it with a generating set of our ideal. Then this module is faithful. Oh, sorry, let me just briefly give a reference for more reading on this last topic. Bosch and Egbali have a paper where they discuss this question, the previous question, simplicity of rings of differential operators and faithfulness of local cohomology. So you can read more there. But let me go back to here, where I'm not assuming really anything about the ring, just domain of positive characteristic, nothing about its singularities. But I'm assuming something kind of strong about, or possibly kind of strong about the ideal. Okay. Yeah, we can quickly go through the proof for the most part. So we can reduce to the case that R is complete, kind of similarly to the argument we looked at before. And to the case where this residue field is algebraically closed. And there's something to check there, but I won't check it now. You can check on your own or with the paper. Okay. And so then there's a map from a complete local ring to R, like so. Okay, so we've got this coefficient field K now, and take the image of the power series ring where we send the variables to the F's. This maps to R, and the maximal ideal is generated by the F's, or its image is generated by the F's, so it expands to I. Okay, so the T local cohomology of R, we can think of R as an A module, and this is the T local cohomology of R with support in the maximal ideal of A. So that forces the T local cohomology of A with support in its maximal ideal to be non-zero. So the dimension of A has to be at least T. Okay, but maximal ideal is T generated, so it's equal to T, and it's a power series ring. Great. Okay, I would like to apply local duality over A. And, well, one reason we cared about the dimension is so we could figure out that we're using the 0th x here in our local duality. So the matless dual of this local cohomology is the Halms from R back to A, A linear Halms from R back to A. And so that means that, well, let me introduce a name here too. Oops. Oh, hi. So the annihilator of this local cohomology is the annihilator of its matless dual, or and just a moment's thought will convince us that if we want, viewing this as an R module, if we want to annihilate all those Halms, then we should be in the kernel of each of them, and conversely. Okay, now let me go back and consider what happens if we replace our generators by some Frobenius power of each of them, or some Frobenius iterate of each of them, same Frobenius iterate of each of them. What happens? Okay. Well, this ring gets replaced by a to the q. Okay. This was a perfect field, algebraically close to perfect, and then we just get the image of this under the eth Frobenius. And the expansion generates an ideal that has the same radical as I. So we're talking about the same local cohomology module. Everything else is the same. So in particular, we can realize this J as the kernels of the Halms, where we replace A by A to the Q. And this is the same ideal. So what if it was not 0? That's our hypothesis. Then we'll take a minimal prime over it. And let me state a fact and or exercise. If P Frobenius power Q is contained in P symbolic power H, so Q is a power P, of course, then R mod P symbolic H is, by the natural action, a torsion-free, finitely generated R mod P image under iterative Frobenius module. So this is naturally a module over here, and the claim is so that it's but that's the case in that it's a torsion-free one as well. Okay. So let us just believe it. For the moment. Okay, so we can also, J is non-zero, then we'll just, of course we can pick a non-zero, and of course we will pick a non-zero element. And we'll pick in a Q and an H that fit that story. The intersection of the symbolic powers is 0, okay, so we can do this. Okay, then if we can do that, because this is a torsion-free R mod P to the Q module, of finite rank. Then it embeds in a direct sum of copies of the ring. Okay, so this is from the fact. And now if we have our non-zero element U in R, it maps to something non-zero in here. Okay, maps to something non-zero, and we can choose one of the factors for which the image is non-zero and project. Okay, so we have such a map like so. And on the other hand, P is a minimal prime of J. So kind of a similar trick to what we were looking at in our first argument. So R mod P embeds into R mod J. Just as well with when we put Q's here. And if we have V in here, okay, same V from here, this maps to something non-zero. And to be non-zero in here, well, that means I'm not in J, or I'm not in J to the Q inside of here. So there's a map from an alinear map from R back to A that sends the image to something non-zero. Oops. Okay, so what do we get when we put it together? Okay. Well, we got an A to the Q linear map from R to A to the Q that sent U to something non-zero. Okay, but that contradicts that U is in J. And great, and that was the proof. I guess it's a good point to end. So thanks for your attention.
Thank you, Jack, for a very interesting talk. We are ready to take questions.
Can I ask one question?
Yes, please.
Yes.
Hi, Jack.
Hi.
So, in your result, which is in the last you have proved,
Yeah.
so in that you are assuming R is a domain, right?
Correct. Yeah.
So, can you remove that hypothesis using some techniques that you have mentioned before?
Well, so the only way that I can improve this that I know, let me write the statement. So same. Okay, so R of characteristic P. I is F1 through FT, and H, so cohomological dimension of I is equal to T. Then, without assuming that R is a domain, the annihilator of this local cohomology module, oh, I should have left a little more room, sorry, then this is an ideal of height 0. So that's the improvement. Yeah, the one improvement outside of the domain case that I know.
Okay.
Yeah, thanks for the question.
Thank you.
Of course.
And can you say something more if the ring is F rational?
Well, I don't know. Yeah, I really don't know how to. Sorry. Yeah, I don't know either how to improve on this strongly F regular argument, or to use the F rational hypothesis in the context of an argument like we have here. Yeah, I don't know. That's all I can say.
In the beginning, you mentioned the connection of local cohomology with the singular homology. I guess the ring that you took was polynomial ring. Did you really mean that, or power series ring?
I did mean polynomial. So yeah, sorry. Let me jump to the statement here. Yeah, I did mean polynomial here, right? So I do want to have access, at least for the way that the statement that I had in mind, I do want to have access to an honest analytic topology. So like Euclidean topology, thinking of C to the n inside of R to the 2n. I'm not sure which, what the appropriate topological statement would be in a power series ring. Perhaps there is one, but I don't know off the top of my head.
Yeah, of course, one could consider the analytic variety rather than algebraic variety.
Oh, I see. Yeah.
I mean,
right. Yeah. So
is it already in Grothendieck, or whose result? Because I read in Grothendieck's notes that Grothendieck wanted to understand fundamental group of complement of an algebraic variety.
Right.
Maybe Kishi may know this. What is the connection, actual connection with the singular homology of complement of the corresponding variety?
Oh, I don't know. Sorry.
Yeah, this is considered in the Hartshorne's notes. I know that, but for fundamental group.
May I ask? So, do you really know need? I can say P. So, how about the result?
Oh, yeah. Thank you. Great question. Yeah, I should have mentioned. Yeah. So for so let me first say that the same statement is false in mixed characteristic. So it's false in mixed characteristic. So Dada, Switzel, and Zhang saw that if you take a triangulation of RP2, take the Stanley-Reisner ideal associated to that, then the top local cohomology module with support of that in a ring of mixed characteristic with residue field, or residue characteristic 2 is annihilated by 2. So Stanley-Reisner. Let me Stanley-Reisner. I shouldn't say ring. I should say ideal of a triangulation. I guess the smallest triangulation. I think that's well defined. Of RP2 inside, and let me just say 2 adic numbers adjoint some variables. The top local cohomology module is annihilated by 2. Of course, it's coming from the 2 torsion and the singular cohomology of RP2. It's annihilated by 2, and this ideal. And so the cohomological dimension is equal to the arithmetic rank. So
You are taking local cohomology with respect to I?
Correct. Yeah. Yeah, so mixed characteristic, this is just false. Characteristic 0. Yeah, we don't know. Yeah, so this so it actually reduces. So the statement where you assume that the cohomological dimension is equal to the arithmetic rank, then it reduces to the case when those numbers are equal to 3. The case of 3 generators. But actually, we weren't able to completely convince ourselves for 2 generators. So even, so, yeah, I don't know. I don't know a counterexample. But...
Oh, thank you very much.
Oh, of course, thank you.
Yeah. So the 3 authors, Datta is Rankaya Datta or SP
Correct.
Datta?
Yeah, Rankia, yeah.
Okay.
Yeah, Dada with the with an A, I guess. Shankar is with a U, I think.
Okay. Yeah, so you are saying that characteristic 0, we don't know a similar result.
Correct. Yeah. So, well, okay.
What is the belief? You expect that to be true?
I'm not sure. I guess I would think I would lean more likely towards yes than no, but I really don't have a good basis for it to say so.
Okay.
Yeah. So one in characteristic 0, it can say it for direct summands of polynomial rings, but that's really not. It's certainly not the best thing that can be said, and that much I'm almost sure.
Okay. Yeah. All right. Are there any other questions? I don't see any questions. So, Jack, I want to thank you once again for a very interesting talk and some good questions for our young audience to work on.
Oh, great. Yeah. Thanks again for the invitation.
Nice to have you. Yeah. So, thank you.
My pleasure.
Yeah.